Hello, welcome to my channel. Today we're gonna talk about the wave function. So first of all, what is a wave function? A wave function is a function of the complex plane, complex space. So this is the most fundamental concept of a wave function. This is of the complex space. And when you compare this to an ordinary wave, this is gonna be almost completely different. So first, let's consider the Galilean transform. So you might already know what it is. You consider two different frames, and S prime. So two completely different frames. And with an ordinary wave, you would have your phi here is a phase of the ordinary wave. It would equal to kx minus omega t. This is a phase. And this guy, when observed in S and S prime, would be the same. So we say that phi would be equal to phi prime. This consequently would make k equal to k prime and omega equal to omega prime. And with these two equal, we can safely say that this is an ordinary wave because when you consider a wave function in quantum mechanics, this guy is not gonna be Galilean invariant and is not gonna be easily and directly measurable. So that would be our conclusion for this part, and this would give us then the matter wave would have all of these would have P equal to HK and E equal to H omega. The phase would be Kx minus omega t, and we would have two different kinds of velocity, as you would see why. We would have V group and velocity of the phase. So the velocity of the phase is easy. It would just be omega over k. And this guy would equal to 1/2 of the velocity. And you would some people would say that this is good enough. But we want the full velocity, not half of it. So we're gonna take a look at the group velocity next. With the group velocity, this guy would equal to the derivative of omega relative to p at k naught, and this guy would be equal to would be the same as e. Oh wait, this is k. dk. This would be the same as the derivative of e relative to p over no need for that. Would be the same as that, and this is basically just the derivative ddp of p squared over 2m. This would give us p over m, and p over m is our desired velocity. So you can say that when we say velocity, we would like to deal with the group velocity and not the phase velocity. Okay, now we're going to talk more about the group velocity. So the definition of a group velocity is that this is the velocity of a packet constructed with like a superposition of wave function. So our group would be written as psi, the big psi, x and t, be the integral of phi k and e, oh my gosh, e to the I kx minus omega t over dk. This would be our group. And you would ask, what is this phi of k function here? And what does it contribute to the whole picture? So this is when we have to talk about the stationary phase principle. So this phi of k here would look something like, let's draw it here, would look something like this, 5k up here and k here. It would be 0 everywhere, and then there would be a big spike up. And this spike would be around k naught, a number. And if you want this part to contribute something, you would need it to be stationary around k naught. You don't want it to oscillate like crazy around here. So it would not eliminate itself. So that is the stationary phase principle. And with this, we get that phi of k is equal to kx minus omega t. And now we're going to try to derive the group velocity from here. So we're going to derive this guy. This guy is going to be k over okay, around k naught. And this is the k out minus omega k naught t. And from the stationary phase principle, you need this to be 0. And to satisfy that, x would need to be equal to d omega dk around k naught t. And from this, we can safely say that our wave function phi psi x of t would equal to psi x minus d omega dt t 0. So from this, we can safely say that when you evolve the wave function through time, the shape would be the shape of it initially minus the group velocity. And the next and the last part is a plane wave, a free wave. A free wave. So the wave of a free particle, or a free wave, this would have, well, E and P, obviously. And with its E equal to H omega and P equal to H K. Well, H bar, actually. It's H bar. And from this, you would get 4 choices as to what your wave would look like. First is the sine of kx minus omega t. Next is the cosine of kx minus omega t. The two last one is the exponential of minus ikx plus I omega t, and exponential of ikx minus I omega t. And so the safe choice here would be these two, as you don't really want to deal with just sine and cosine alone. So both of these are safe. So you can choose either of these. And these would be the matter weight of a wave function for a particle with momentum P equal h bar k and energy equal to h bar omega. So that's it for today. Goodbye.